Hey everyone, welcome back to this course. In this week's module, we're going to be taking a look at phasor diagrams, the power triangle, and power factor. So let me go ahead and share my screen here. All right, so we're looking at phasor diagrams, power triangle, and power factor. So where did we leave off? So last week we introduced the impedance model, and we arrived at some result, right? So the voltage in AC steady state is given by some current times whatever impedance, the impedance of the device or network that you're looking at is, right? And so from this, we can go ahead and look at the different plots of the various devices, right? So for the resistor, we arrived at VR is I times R. And so what does this look like just maybe in this complex plane, right? So VR in the complex plane has some real part and some imaginary part, right? So we're looking at what is VR's representation in this complex plane? Well, actually, it doesn't have any complex parts, right? It's completely real um, if we're just looking at the magnitude of this current source here. So when it's completely real, right, it has kind of this phase angle or this angle of 0 degrees. So here's our VR. So now if we take a look at the capacitor using the impedance model, we came at this result that the capacitance is given by I times 1 by, we'll just do J omega C. And so we can rewrite this. If we multiply through, and so if I multiply by J to give us maybe something a little more telling here, we have I times J divided by, so J times J squared is minus 1, so minus omega C. And so we have this negative I, negative Ji times 1 by omega C. So this voltage is now completely complex. Sorry, it's completely imaginary here. We look at the real axis, we look at the imaginary axis, and VC is given by some negative imaginary value. So it's going to be going down, and this is our VC. And you can see that this is negative 90 degrees out of phase if we assume that the resistor is our reference here, right? So 0 degrees there. And lastly, we can take a look at an inductor. So we arrived at the impedance model for the inductor, I times J omega L. And we don't really need to do any fancy thing with this one to see that if we plot this on the complex plane, real, imaginary, this is also completely imaginary, but instead of negative, it's positive. So this is at an angle of a positive 90 degrees, with respect to this real axis here. Right, so we can see that the voltage, or rather the current, right? So we're looking at how the current is being scaled with respect to the reference voltage there. So that's all good. And, once we have this kind of impedance model in mind, we can take a look at one of the circuits that we've been analyzing and kind of make sense of the response that we observed in lab. So let's take a look at this RLC branch. And, I'm going to go ahead and also introduce this load resistance, not load, sorry, the source resistance. Right, so we found in lab a number of times that these power supplies and function generators that we are using actually have some internal resistance. So we'll just go ahead and model that by some R Thevenin. And this has some V Thevenin, right? Because by Thevenin, we can reduce any network into a voltage source in series with this resistor. And so this side, this is our load. This RLC branch here is our load. And it doesn't have any active components. It doesn't have anything that's supplying power into the circuit, right? If we only had this load, then power would just completely dissipate and go away. But since on the other side, right, this is our source on the left of this, we have some kind of input. We've got some voltage source that's constantly driving the circuit. Well, we can reduce this into some Thevenin equivalent circuit, right? It wouldn't make much sense to reduce the load into some Thevenin since there's nothing that's supplying power. So this is our source, and we model it with some R Thevenin and some V Thevenin. I'm just going to call it VI for that input. And so this is the RLC of our load. And from here, we can go back into the complex plane. And instead of real and imaginary, I'm going to write this down as I and J times I. And that's simply because we had that V is I times Z. And this can take the form of I, plus JI. The current has some real and some complex value, or in some imaginary value there. So we're going to plot it like this. And we're going to start off by looking at the Thevenin voltage. Right, so the Thevenin voltage is simply is just completely real. It's on this I axis, right? So where I is the real part of that current. And then we're going to plot and so this is VRTH. And then we'll go ahead and plot I'm going to plot the inductor first, maybe. So we're going to go up. We're going to go up some. And so VL. And then we're going to go right more. VR. And then we're going to go down due to this capacitor. This is VC. And that's just from this thing that we had where any resistor is completely real, any capacitor is completely negative, right, in the imaginary direction, and any inductor is completely positive in the imaginary direction. So now we have, right, we've got these few vectors here, and this distance from the origin to wherever we landed should give you the voltage of the source. Right, so it'll give you that magnitude, and it'll tell you how many degrees out of phase that it is with respect to that output across the capacitor there. So hopefully that's a little bit informative on how you go about constructing these phasor diagrams. I think we'll have like one little example of how to practice using this in the exploration, but other than that, it's not entirely useful here, I'd say. So the next thing that we want to talk about is the power triangle. Right, so from this kind of like phasor notation, we always have some real component and some imaginary component. And by the Pythagorean theorem, the real squared plus the imaginary part squared, square root of this, gives you that hypotenuse, right? So the imaginary component is always orthogonal to the real component there. So he's at this 90 degrees, which allows us to use that Pythagorean theorem. And so there's an impedance triangle where you just look at the real and imaginary parts of the impedance. But there's also something called the power triangle, right? So power, again, in general, is I times V. And when we take this product into the complex domain, we also have to consider the conjugate. So it's I times V conjugate, which is the same as I conjugate times V, right? Where this asterisk is the conjugate. And just as a reminder, if you have some A plus BJ, then the conjugate of this is A minus BJ, right? It's just you take the opposite part of the imaginary component. But in any case, power in the complex domain is given by these two equivalent statements, right? And so we define this new concept called the complex power. And the complex power is the sum of the real power, P. And I'm sorry. So what I just defined here is the complex power. So this is S. S is I times V conjugate, which is also V, I conjugate times V. So it has some real part, capital P, and it's got some imaginary part, capital Q, where P is the real power, and Q is the reactive power. So the real power is anything that's dissipated by, resistors or any kind of equivalent resistance in our load. And the reactive power is kind of just the energy it's representative of the energy that's sloshing around between the energy storage elements, right? So like the inductor and the capacitor. Right? So when we just took a look at the transient response of this RLC branch, you'll remember that the energy was just sloshing back and forth, and it gave us that oscillatory response. So that would be some way to visualize the reactive power versus the real power. And so the real power is usually what we see at the end, but reactive power is just, we need to keep it in mind. But in any case, so going back to this real and imaginary model, so we have real power in the horizontal, the real axis. We've got reactive power on this vertical axis. And we have this magnitude of the complex power here. And so that's going to be P squared plus Q squared, square root of all this. So hopefully that gives us a good idea of this power triangle. It's I think a lot of people get confused by it, but it's a pretty straightforward concept, I think. And so if we had like the reactive power, or the complex power rather, we could find the real power by taking this times cosine theta, where this angle here is theta. If we had if we had any two values, we could find the rest, basically. So Q here is S, the magnitude of the complex power times the sine of theta. And we have this thing called the power factor, PF, which is simply the cosine of theta. And so why do we care about power factor? Well, we want to reduce the amount of reactive power, because any kind of reactive power, right, is just sloshing back and forth through the system, and it's not really being dissipated in our target. Right, so it's just going back and forth. It can lead to some kind of harmonic distortion, right, by sending energy back into the source, and it creates a whole mess of problems that we don't want. So our main goal is to drive this power factor. So I'm going to write this down. We want to drive the power factor PF to unity. And that just means to 1. So when we have a unity power factor, that means that this implies that theta goes to 0. We want to get that angle down to 0. And that also implies, right, that we want to get rid of the reactive component here. We want to drive that reactive power to 0. And lastly, right, so all the power is real. And so that's just a little spiel on power factor goal, why we care about it, and what it is pretty much. I think that should be sufficient for what we're going to be talking about in lab today. I'm not sure that I need to go over more LT spice or anything. This should probably be the only tutorial. So thanks for tuning in. See you guys next time.